Hi, this is Dylan doing chapter 12 explanation for chapter 12 homework. So starting with number 1, we are given this equation, f equals 81,000 minus 27,000 times v. From that point, we can basically manipulate. We want to pull the force equals mv dv dt because it's f equals ma, but we are changing acceleration to the derivative of velocity. And then we take the distance equation up top here. We plug in our values from what we know. And from there we integrate that. We simplify it a little bit first, then we integrate it from v1 to v2 or v2 to v1. And from that point, let's see. Yeah, so that's correct. And then we get our time, 18.83 seconds, after we integrate from those two things. And then that was the derivative with respect to time. We do the same thing with the same equation. However, we take the derivative with respect to position, which would be dv dx instead of dv dt. And then we plug all of that in. We integrate from the same values, 2.5 to 1 meters per second. And then we're able to pull our x value and find the distance traveled during the time interval. All of these problems also took me at least an hour each, so I don't know how much detail you want us to go into explaining these. Number 2, part A. So basically we just need to write down, after creating a force diagram for the two separate objects, we needed to create a kinematic equation that would give us that force between the tires touching the ground. So that's going to equal my 2t, and then I have the force of friction and then tension pulling on the opposite direction. And from there, let's see. From there, I was able to find tension and then plug it back into one of the two kinematic equations that I had and find friction. And then since I knew that, I could do the sum of the forces in the y direction with my first equations there, remanipulate it and find the force between the boulder and the pallet itself. I had to draw a new free body diagram and solve there. Number 3, this one, let's see. We basically, we know that mv squared over r is going to be for circular motion. And then we know that the 450 gram tether ball is offset by some angle. And so instead of plugging values in right away, basically we're just manipulating the equation F equals ma the momentum equation. And this one took me forever to figure out because I didn't know that you could use a sine or cosine or another factor as a quadratic formula for the variable. So then I just plugged that in and got my theta. But that took forever to figure that out. It's ridiculous. Moving on to number 4. I was basically able to draw my free body diagram. I would start it at point C. When the ball was at point C, I knew that velocity was 0. I took the offset for the mg, or 130 pounds, pointing downward with the 20 degrees. I wrote the sum of my forces in the y direction, and solved for those. And I was able to get the tension in the rope from the ball up until the mounting point. And for part B, at the very bottom of the swing, it gave us velocity, which was nice. So I basically just looked at my free body diagram at B, drew a new one, and did sum of forces in the y direction, and was able to find the tension at that point. Number 5. This one took a while as well, in order to understand the difference between tangential acceleration and normal acceleration. That was something that I needed reviewing for me from physics, because half this stuff is not taught in any other class, so this is the first time. So on this one, basically you can see my free body diagram up top. I have my static diagram and then my kinetic diagram when it's moving. So I was able to do a sum of forces on the plane, like the flat plane. You could say the X and Y plane in 3D. And then I was able to factor out the mass, cancel that because it eventually cancels with the force of friction because the normal force is mg. M is gone. I'm left with the coefficient of static friction divided by my tangential and normal acceleration. Divided by gravity. I was able to find the static friction from there. However, I did not have my normal acceleration. So I had to use kinematic equation, v final equals v initial plus acceleration times time, and plug in all of my knowns, and then plug that into my normal acceleration formula, which is in yellow there. And then I could find my static friction. And yes, number 6. This took a lot of just knowing and finding the orbital motion formulas. As you can see, they're all circled above there. And so I had to convert everything from kilometers per hour to meters per second, or just meters. And so I was able to use F equals big G, big M, little m over R squared. Since we had all of that information, according to... Oh, wait, am I thinking of the wrong one? Nope, that's correct. According to Venus, oh, I was looking at the wrong diagram. So then I was able to plug in the mass of the Earth, the mass of Venus over R squared, and R squared was the radius between the center of the Earth. Let's see, where did I write that down? I feel like some of my stuff got erased, maybe. Oh, it's right there. So then I was able to find the mass of the sun. And so basically I had all of the information I needed to find the mass of the sun based upon that equation. And from there, I was able to redo that, use the same equation, but in this time, the acceleration on the sun was going to be technically the gravity there, so I changed it to G, which is a little confusing, but so yeah, previously I had F equals big G, big M, little m over R squared. I was able to plug in the let's see, let me draw that here. That's where that came from. I just wrote it over there. I know that the normal acceleration was v squared over r, so then I plugged that in because it equals F equals ma, but I made that my normal acceleration, plugged the normal acceleration definition in for acceleration on the left side of the equation, plugged everything in, got the mass of the sun. Did the same thing for B. However, the radius is going to change in the denominator, so I changed that and was able to get the acceleration this time, which I was solving for instead of the mass, for the sun, which would be the normal acceleration going inward or other known as its gravity. Number 7, this one was also a bit confusing, but there's a lot of equations that equal each other, and so I knew that basically, let's see, it asks for, I know that U equals 1 over R. So then I plugged that in for this part of the equation. So I have 1 over R squared in the denominator. I manipulated the equation and brought that up top so that I didn't have a fraction in the denominator. And then from that point, I just plugged everything in and solved for f. And then that was the proof there, showing that it is inversely proportional to the square of the distance, as you can see up top there. So that was number 7. The 1 over R was the key there. Just plugging that in for U and remanipulating. Number 8. Oh yeah, this one's just great. I actually understand this one very well now, but at the time this one took me about 5 hours. So there's lots of work here. Part A is in green. I knew that I needed to find the escape velocity, or in other words, the equation for the parabolic escape velocity, and I needed to find the escape velocity of a circular or ellipse, which that was very confusing to me between 2D and 3D. But same equation, same thing. So I was able to find the escape velocity of the ellipse or the circle. Yes, the circle. And from that point, I plugged it into the escape velocity for a parabola. Then I knew the 2 different speeds at point A right when it was going into parabolic orbit or a circular orbit. I subtracted those, got the difference. And that's part A. Part B, there's this equation, H over RA. So that's the radius at point A in the denominator. I'm confused of what the H is, where it comes from. And yes. And so I was able to use that, and I was able to use the relationship that we proved. Let's see, where did we prove that? We prove it in number 9 below. This relationship down here, 1 over RA plus 1 over RB equals 2 GM over H2. I didn't write down, oh yeah, so in yellow over here, this is the relationship. For a ellipse, and so then I took GM over H2, 1 plus C cosine theta. I'd put it in terms of C, and let's see, I know that whatever cosine is at point B, it's just some value. But I know that 180 degrees from that, it's just going to cancel out because they're just inverses of each other. So then that gets rid of the c cosine theta A and theta B, leaves us with 2gm over h squared right here. And then I get like terms in the denominator for those fractions on the left side of the equation, because that's what they equal. And solve for h, plug in all of my values after converting a lot of them to kilometers, or let's see, yeah, after converting them, and then I get h, and then from that point, once I have h, I take it back to the original equation up here that was highlighted. Velocity of an ellipse is h over ra. Plug in my h and my radius at point A and get my velocity, which would be the velocity at point A that it needed to be at to enter an elliptic orbit, or sorry, that's in the parabolic orbit. Let's see. A little confused there on what this value is, but I know it's at point A. I'm not sure if, I think that's the total velocity, and then I need to take the velocity of, oh yeah, that's for the parabolic velocity. I just get confused because I name it v ellipse. And then I need to subtract that from the velocity it would be at entering the circle, and then that's how much it would need to slow down, is the difference there. Part C, it asks for the eccentricity of the elliptical orbit. Solving number 9 really helped me understand 8, so I probably should explain that better, but I know that there's a relationship between these 4 things. So I took the 2 important ones that I needed, this one and this one, set them equal to each other because that's the relationship, plugged in all of my values that I already have, and I needed to figure out what C was, solved for C, and then plugged that into my eccentricity formula right here and got the eccentricity. Okay, that's number 8. Took me 5 hours. Number 9. So again, I know that at the perigee or apogee of this orbit, I know that I have the relationship 1 over r blank subscript equals gm over h squared plus c cosine theta a. Since they are inverse to each other, 180 degrees at point B would just cancel out with A. So that's gone. And then I am able to plug those back into the equation that it gives. Cancel a few things, the 2's, and then I'm back at the original equation, which proves that the curvature of the orbit at those 2 points can be expressed either way. The one it gives me or the one in my answer. And that is chapter 12 homework.